Module 9, Section 7.3, Basic Counting Principles. Objectives: be able to apply and use the multiplication principle. Objective 2, apply and use the addition principle. Multiplication principle. To illustrate this principle, let's start with an example. Suppose you have 4 pairs of pants in your closet, 3 different shirts and 2 pairs of shoes. Assuming that you must wear pants, a shirt and shoes, how many different ways you can get dressed? Here is a solution. You have 4 choices of pants and 3 choices of shirts here. For each pair of pants chosen, you have 3 options for shirts. You have 12 equal to 4 times 3 options for wearing a pair of pants and a shirt. Now with each of these 12 options, you have 2 pair of shoes to choose from. Thus you have a total of 4 times 3 times 2 equal to 24 options to get dressed. This is another way of looking at the same example. So we have 4 ways of selecting a pants, 3 ways of selecting a shirt, and again 2 ways of selecting a pair of shoes. So this will actually indicate all possible ways we can get dressed. So there are actually 24 different ways, which is equal to 4 multiplied with 3 multiplied with 2. So this diagram is what you call a tree diagram. We are going to generalize this. Suppose that a task can be performed using 2 or more consecutive operations. If the first operation can be accomplished in m ways, and the second operation can be done in n ways, the third operation in p ways, and so on, then the complete task can be performed in m multiplied with n multiplied with p and so on ways. So we are multiplying all these numbers to get the total number of possibilities. Here is an example. How many different ways can a team consisting of 28 players select a captain and an assistant captain? Selecting a captain. If all team members are eligible to be a captain, there are 28 ways this can be done. Selecting an assistant captain. Assuming that a player cannot be both a captain and assistant captain, there are 27 ways this can be done, because there are 27 team members left who are eligible to be an assistant captain. So now using the multiplication principle, there are 28 multiplied with 27, which is equal to 756 ways to select both a captain and an assistant captain. Next example. How many 8-letter code words are possible from the first 12 letters of the alphabet if no letter is repeated? So it's an easy way of calculating this. We have 8 letters. We have 12 letters to choose from. So the first letter can be any of the 12. We are assuming that the same letter cannot be used. So we only have 11 letters. So there will be 11 possibilities there. I cannot use the first 2 letters here. So there will only be 10 possibilities and so on. So this will be 9. This is 8. This is 7. And then 6 to choose from. And the last letter can be any of the remaining 5 letters. And using the multiplication principle, I need to multiply all these numbers to get the answer. So 12 times 11 times. When I do this, I will get the number. So that is going to be the answer to the first one. What will be the count if the letters can be repeated? If the letters can be repeated, the first choice will be 12. Second choice is also 12 because we can use the same letter again. So that way it will be 12 times 12 times 12 multiplied 8 times. So the answer will become 12 to the power 8. If adjacent letters must be different, how many ways we can create 8-letter code words? So this is just a display of one of such code words. So when we do the counting, the first letter can be any of the 12, second letter should be any of the remaining 11 because they need to be different, and the third letter can be anything other than the second letter, so that opens up 11 possibilities there. and the fourth letter will be anything other than the third letter, so that opens up 11 possibilities. So like that, we need to multiply 12 times 11 times 11 times 11 times. So the answer will be this number up here, 12 times 11 times 11 7 times. So this will be, so we can also write this as 12 multiplied with 11 to the power 7. There is one more example. How many different license plates are possible if each contains 3 letters followed by 3 digits? That is 0 to 9. This is how a license plate will look like. We have 3 letters followed by 3 digits. We are going to count it. First letter can be any of the 26 letters. Second letter can be any of the 26 letters because we can repeat the same letter. Third letter could be any of the 26. The first digit could be any of the 10 digits. Again, because we can repeat the same digit, so the second digit can be any of the 10 digits. The third digit will be any of the 10 digits. To get the total count, we need to use the multiplication principle. So the answer will be 26 multiplied with 26 multiplied with 26 multiplied with 10 multiplied with 10 multiplied with 10. Also written as 26 to the power 3 multiplied with 10 to the power 3. Objective 2. Addition principle for counting. We introduce the following principle of counting that can be illustrated using a Venn diagram. Number of elements of A union B is equal to number of elements of A plus number of elements of B minus number of elements of the intersection. Notice that in this Venn diagram, when we count A, the intersection will be part of A and it is also part of B. So we need to subtract the number of elements in the intersection once in order to get the number of elements of the union of A and B, which is what this formula is all about. To see how sets play a role in counting, consider the following example. In a certain class, there are 23 majors in psychology, 16 majors in English, and 7 students who are majoring in both psychology and English. If there are 50 students in the class, how many students are majoring in neither of the subjects? And how many students are majoring in psychology alone? We can do this question easily by using a Venn diagram. From the problem, we know that there are 7 students who are both psychology and English majors. So this region will be 7. Because we know that there are 23 psychology majors, we can subtract 7 to get 16 students like this shaded region there. And 16 English majors, if we subtract 7 from that, we will get 16 minus 7, which will be 9. So that will be that part. So these 3 numbers will be adding to 32. Remember that there are 50 students in the class. So if we subtract 32 from 50, we are going to get 18 as the answer for the first question. How many students are neither psychology and English majors? To get the psychology majors alone, we need to look at this portion of that set, which is counting as 16. So the answer to the second part of the question will be 16. There is one other example we can do. A group of 140 people touring Europe includes 63 people who speak Spanish, 75 who speak German, and 8 who speak neither language. How many people in the group speak both languages? So we are going to introduce a Venn diagram here. We have 2 sets represented as Spanish speaking tourist and German speaking tourist. So what we are trying to calculate is the number of members in this intersection. This is S, this is G. So the question will be like, what is the number of elements in S intersection G? It is given that 8 people do not speak Spanish or German. So we can calculate number of elements in the union of S and G to be 140 minus 8, which is 132. Number of elements of S union G will be equal to number of elements of S plus number of elements of G minus number of elements of S intersection G. Substituting the values, 132 here, number of elements of S will be given in the question 63, and number of elements of G will be 75, which is this number up here, and then subtract number of elements of S intersection G. So this happens to be the only unknown here. So we can actually solve this equation. 132 equals 138 minus n of S intersection G. So that gives you the answer to the question. N of S intersection G equal to 6.